Hi, I am Danilo Carastan Santos, and I'm going to present our work entitled Accelerating Machine Learning Algorithms with TensorFlow Using Thread Mapping Policies. And in the context of high-performance computing, it is quite a common practice to use parallel execution in the form of multi-threading, meaning that we have a parallel processor and we use and the applications are constituted by many threads of execution, and they try to run into this parallel processor in the parallel manner, meaning they try to process at the same time. And the point here is that since they try to run at the same time, they often compete for resources of the architecture. So they compete for the cores themselves, they compete for the caches, for the memory controllers. And one problem that rises into this scenario is that by performing different assignments of threads to cores, processing cores, we can either increase or decrease performance. And this problem is the problem that we call the thread mapping problem. And here, just to review, thread mapping is a technique that maps threads to cores considering a certain policy. And a good policy is the one that effectively makes an assignment of threads to cores that lowers the competition of threads, the competition of resources between threads. And this competition is with lowering this competition, we can make a better usage of the infrastructure of the architecture. So we can we can lower the latency when sharing data. We can have less cache misses, among many other benefits. And this thread mapping, so applying different thread map policies, is often a quite inexpensive technique, and in fact effectively improve performance of different applications. And here the applications that we are concerned are machine learning applications. So here, just briefly to summarize, machine learning is a broad set of automatic methods for finding patterns in a set of observations of a certain phenomenon. And after we find these patterns, we try to use these patterns that were obtained automatically to perform predictions about future events around this phenomenon. And many algorithms in the literature have been proposed in machine learning, and machine learning is being a powerful tool to perform predictions and perform many tasks, such as tasks in image processing, computer vision, autonomous driving, natural language processing, and many others. And one characteristic of the machine learning is that the processing of the applications is often quite computationally expensive, and often practitioners use accelerator devices such as GPUs to increase performance. And in the context of GPUs, while indeed GPUs significantly accelerate performance of machine learning algorithms, it is not as straightforward to perform these to get better performance. First, you need to have the device available to run your application. Not only that, sometimes you need as well to change the application source code. You need to change the algorithm to fully exploit the GPU, and this is some task that can take some time and effort to be done. And in this work, we are concerned about the CPU performance, CPU processing, and we don't want to have use accelerator devices in this task. And the CPU continues to be an important device to perform processing. And while many works already explored this thread mapping policies with traditional multi-core applications, it is still unclear what can we expect when we change the thread mapping policies of machine learning applications, here specifically taking into account the TensorFlow machine learning applications. So we don't know clearly what can we expect by changing policies and by how much can we either increase or decrease performance. And this is the main goal of this work. So we want to run machine learning applications with TensorFlow and in a CPU and check by changing the thread mapping policy how the performance improvements or not improvements we can achieve. So here, just to clarify the idea of thread mapping policy, here we illustrate three different thread mapping policies, which are the ones that we use in our experiments as well. So we have the scatter and the compact and the round robin thread mapping policies. So as you can see here, each policy has its own logic for the assignment of a process to cores, and each of these policies they can result in a different in different usages of the architecture of the hardware. So one can make a better use of the cache or the interconnection bus and so on. So it is and these if these changes result in a better performance or not, it depends as well on the application that's being executed in these threads. So it is important for us to experiment and see by performing experiments which of these policies can result in better performances or not. And for the machine learning applications, so we use this benchmark called AI benchmark, which comprises several artificial intelligence and computer vision tasks. They use recent machine learning models, and these benchmark is built on top of the TensorFlow library. Which I forgot to mention, it's a quite common machine learning library that people use in machine learning. And this benchmark is initially built to test performance on mobile devices and machine learning on mobile devices. And this means that we have a reduced training and test data sets. So the processing of the models and the models and the algorithms they take less time, which is good. Sometimes machine learning algorithms take either hours or days to process, and also enables CPU only processing of these models and algorithms. And of course, this benchmark is publicly available as well for you to check and test as well. And so, as for the experiments, so the experiments that we performed, so we took this benchmark and we executed this benchmark in a dual socket CPU, in a dual socket computer, and we changed for each execution. We changed the thread mapping policy, and we collected the performance in the execution time of the benchmark of each of the thread mapping policies. So here in more details, for each configuration of thread mapping policy we used, we performed 10 repetitions of this 10 repetitions of the execution of the benchmark, and for each of these 10 repetitions we collected the execution time, and then we in the next set of results we report the means of these the means and the confidence intervals of these executions. And we separated the benchmark into two phases. The first phase is the training phase, which is the first step that we optimize the models taking into account a certain training data. That is, we try to find patterns of a given set of observations. And we also have the inference phase, which is given the optimized model, given the learned model, we try to use the model for its purpose. So we try to make predictions of future events regarding the purpose of the model. And all of our experiments are publicly available in our repository, and you are more than welcome to check our scripts and our data and our results as well. So here we have the first set of results, and this figure represents the results that we obtained in the training phase of the benchmark. So in the x-axis we have the different machine learning models that are present in the AI benchmark, and in the y-axis we have the performance improvement in the execution time in comparison to the default thread mapping policy of the machine. So we can see here for the training phase we achieved the significant performance improvements of AI benchmark. So we achieved up to 46% improvement in the training phase of this benchmark. And we also notice here that most of the computer vision tasks here represented by the Inception and the ResNet models, they were the ones that benefited the most of the thread mapping policies. And we also noticed that the scatter and compact policies, they consistently either increase performance by a large margin, or at least they don't harm the performance of the benchmark, as opposed to the round robin policy that okay, sometimes it increases performance nicely, but there are some cases that in fact effectively decreases the performance of the models. And this second set of graphs, this second set of results is for the inference phase of the benchmark. So here, similarly to the training phase, we also achieved performance improvements up to 29%, not as large as in the training phase, but significant nevertheless. And again here, the two policies, either scatter and compact, they seem to consistently either increase performance or not harm the performance of the algorithms and models. And again, the round robin, some cases it increased performance by a small margin. In one case it increased by a lot, but often decreased the performance of the models. So here, to summarize, we noticed that okay, by making different assignments of threads to cores, taking into account machine learning algorithms developed under the TensorFlow library, we can in fact increase the performance of these applications. And in our experimental campaign, we found that we achieved up to 46% performance increase in the training phase, and 29% of performance increase on the inference phase when compared to the full thread mapping policy of the platform. And these performance gains are interesting because they can be achieved by just changing an environment variable of the system. You don't need to have a different device, an accelerator device. You don't need to buy an accelerator device and also change the code drastically change the code to make the applications run faster, which is quite interesting. And for future research directions, of course, at this first step we noticed the differences we make it a little bit clearer on what can we expect by changing thread mapping policies, but we also need to understand why a certain thread mapping policies results in the better and better performances. And for that, we can use hardware counters during the execution to extract more data about the application's execution and get insights from that. And we also can take a deep look at the machine learning algorithms and check if there's some correlation between the architecture and what's being processed in the threads, to see if a certain policy takes advantage of that. And another interesting research would be to check if this how by changing the policy, what can we expect if you change the thread mapping policy, if these thread mapping policies were available on mobile devices as well. So, and this is interesting because machine learning on mobile devices is being a hot topic, and we have in fact already some machine learning libraries that run in the mobile devices, such as TensorFlow Lite. And if you have the option to change the thread mapping policy on mobile devices, what can we expect in terms of performance, which would be quite interesting to increase performance of mobile on mobile applications by just changing one policy. This would be quite interesting to look for as well. And here is just to thank all of our funders and sponsors to make this work feasible. And that concludes my presentation, and I thank you very much.